So probably the most common type of phenomenological force that you'll encounter is restoring forces or spring forces. Okay? Now if you recall drag and lift and friction, drag, lift, friction, or these kinetic friction, all have to do with what your motion is. They're related to how fast you're moving or in what direction you're moving. Spring forces or restoring forces have to do with what the current configuration of the system is. So they have to do with what the position is, not what the motion is. You're used to sort of seeing springs a lot, right? You dealt with them in design nature, so it's the sort of conventional picture for a spring is something like this. So if we imagine a spring that's connected to a wall here and is connected to some mass here, we could imagine that there's some sort of normal length of the spring, which we typically call L naught, and that spring is going to pull the mass back if the actual current length of the spring is greater than L naught, and it'll push the mass forward if the length of the spring is less than L naught. And so to think about our sort of situation, but also what our magnitude and what our direction is, the magnitude of the spring force is what's called the spring constant K times the length of the spring minus L naught, and the direction of the spring force is whatever direction brings you back to equilibrium. So in this particular case, let's think about what that is. If L is greater than L naught, the force will be in the minus I hat direction. So this is I hat. So in this particular case, my spring force will be minus K times L minus L naught times I hat. That says that when L is greater than L naught, did I just make a mistake? I think I just made a mistake, didn't I? No, when L is greater than L naught, this term is positive. That means the total force is negative in the I hat direction. When L is greater than L naught, it gets pulled back. Similarly, when L is less than L naught, this term will be negative. Negative times negative is positive. I get a positive force in the I hat direction. And finally, when L is equal to L naught, the net force is 0. Now, it's worth noting, or it's worth sort of thinking a little bit about why is this so ubiquitous? It's such a bad idea to use words like ubiquitous when you're trying to write things by hand because you really are never sure what the spelling is. And there's actually a fairly deep kind of mathematical reason for why it's ubiquitous, and it has to do with Taylor expansions, right? If you think about, consider the case of any object that's at equilibrium. Well, what do we mean by equilibrium? What equilibrium means is that if you displace the object from that position a little bit, it'll want to return to that. Okay, so I actually should say this is at a stable equilibrium. So the sort of idea would be like if I imagine having a marble, right, in the bottom of some bowl, right? The bottom of the bowl is the equilibrium point for that marble. If I displace the marble up to here, it'll want to roll back down to the bottom. And in fact, what will happen is it'll roll back and forth and it'll gradually lose energy and it'll return to equilibrium at the bottom of the bowl. So this would be where the stable equilibrium is. Now, if an object's at stable equilibrium, what does that mean about the net force on the object? Well, it's not moving, so that means that the net force on the object must be 0. Well, let's imagine sort of displacing the object a little bit away from that equilibrium point. When I displace the object a little bit away from that equilibrium point, if I say the force at point x is 0, and ask the question, what's the force at point x plus delta x? So I displace a little bit from that equilibrium point. What do I expect the force to be? Well, I don't know what I expect the force to be, but I could think about this just as a function and say, well, how might that behave? And I could use a Taylor expansion, right? I could say, okay, well, f at x plus delta x has to be approximately whatever the value of F is at x, right? Plus, some derivative, however F, the force changes, times delta x, plus other terms, right? And those other terms will depend on delta x squared, delta x cubed, right, and so on. You can do this expansion. So, but I know that the force at the actual equilibrium point is 0, right? So that means that the force, whenever I displace from equilibrium a little bit, the first term in that force is dF by dx, some constant, times delta x. In other words, it's k times delta x. And if I actually think about what must happen here when I displace to the right a little bit, it must come back. So a positive delta x must give me a negative force. So an approximation for my force for any object that's close to stable equilibrium is simply minus k times delta x, where delta x is the distance from equilibrium, which could also be written as minus k times x minus x naught, where x naught is the equilibrium point. Okay? So that's sort of a reason to think about why this k times L minus L naught expression shows up so much. It's actually that it's the very first term. It's the simplest possible way to get behavior that says whenever I go away from equilibrium, I need to come back to equilibrium, right? That sort of makes sense, that a linear model would be the simplest one that would bring you back. Now, it's also worth just thinking about direction here. So let's do a little aside on direction of the spring force. The direction of the spring force has to be oriented along the spring. So you might think about some sort of general situation where I've got some object that's on a spring and the spring is oriented in some way. I could define a vector s hat that's a unit vector along the spring, in which case I would be able to say that the force for this case would be minus k times L minus L naught times s hat, right? S hat tells me what the orientation of the spring is. L minus L naught tells me what the length of the spring is and the rest length of the spring, and then k is the spring constant. Quick note on units here. K has units, of course, of newtons per meter because force has units of newtons.